All right, here's a little problem I encountered recently that gave me pause because it generates what appears to be a paradox. Uh, Produce scale at a supermarket uses a stretch spring to indicate the weight of fruits and vegetables. And then it gives you 5 oranges, gives you the total mass, says they're placed in the scale, excuse me, and the string will be stretched 2.3 centimeters. What is the force constant of the spring? Well, okay, say here's the empty uh, vegetable pan, and here is another picture of it. And let's say we put the oranges in here, and I'm going to represent them by just one mass like this. Here's the oranges. So it stretches the spring down to here, and when you get down to this point right here, the weight of the oranges, which I'm going to call mg, is equal to the force that the spring exerts. And we're assuming this is a Hooke's law type spring. So this is the force due to the spring. Force due to the spring, magnitude of it is equal to kx, and the force due to gravity is mg. So when those are equal, when that's equal to mg, then I can just simply solve that and say k is equal to mg over x. And if you plug in the numbers, you got 0.76 kilograms, 9.81 meters per second squared, divided by the distance that it stretches it, x naught, make that x naught, and that's equal to 0.023 meters, and that works out to be about 324, approximately 324.2 newtons per meter. So that's the correct answer. But the book says that the answer is this. Well, they both can't be right. So if you look at what the book says, they said, okay, let's use energy considerations to solve this problem. And they said, all right, if I'm up here, I have a certain amount of gravitational potential energy with respect to this level right here of mg times x naught. And when I'm down here, I have no gravitational potential energy, but I have spring potential energy. And they're saying that mgx is equal to 1/2 k x naught squared, where that's the potential energy in the spring. Now, if you solve this for k, divide out one of those, multiply through by 2, and then divide by x naught, like that, k then is equal to 2 mg over x naught, and that's approximately equal to 648.3 newtons per meter. And that's what the book got. So what's going on here? What's the problem? They can't both be right. Well, it turns out the problem is if you start here, and let's assume this is a fairly weak spring, so it'll give you a little more of an intuitive feeling for what happens here. If I put this mass in here, I'm holding it, and then I drop it, then it's going to go from here down to here, but it's not going to just stop at this point. It's going to continue on down to some lower point, and then it's going to oscillate back and forth. And it turns out that it goes down by an amount x naught, comes back up to an amount back to the starting point, and it oscillates back and forth across this equilibrium position that we already found, or we could find from this equation right up here. So what's the problem here? Why isn't this true? This mg x naught, it's not equal to 1/2 k x naught squared, and that's the problem. The problem is because I start off with mg x naught, I drop this thing, and when it gets to here, it is true that there's no potential energy, gravitational type, and there is spring potential energy, 1/2 k x naught squared, but there's also kinetic energy. So the real case is mg times x naught is equal to 1/2 k x naught squared plus 1/2 m v squared. Now, if you knew what v is, you could solve this equation, and you could solve it for k, but you don't really know that. So how can we fix this? Actually, if you're satisfied that the paradox is understood at this point right here, by realizing that they're ignoring the kinetic energy in this problem, then you could stop right there. But if you want to look at it a little bit further to see how to resolve this, think of it like this. In a real situation where you're putting this mass here, you're holding it with your hand, and you're exerting a force upward in this direction, which I'll call the force due to the hand, and you're just lowering it down to this point so that when it gets down here, yes, there is no more gravitational potential energy, there's no kinetic energy. But the way to look at that is I started off with mg x naught, gravitational potential energy, but I took energy out of the system with my hand because I'm exerting a force opposite to the direction of motion, so I'm doing negative work, and it turns out that that negative work is just equal to 1/2 mg times x naught. And then when I get to the bottom, I don't have any kinetic energy, so this amount of energy was converted into the spring potential energy. And this means then that 1/2 mg x naught is equal to 1/2 k x naught squared. And then this, of course, leads to mg is equal to k x naught, so that k then is equal to mg over x naught. And that's the same answer we got before. And if you want to see how this is true, the amount of work done by your hand in moving from here to here so that you get down here with no kinetic energy, then look at the next video for that. All right, this is a continuation of the problem concerning the produce in the scale that I just got through working a few minutes ago to show you how to handle the how to determine what the spring constant is using energy considerations. And one of the factors was that I said the work done by your hand in quasi-statically lowering the mass from this level down to this level, that work done was minus 1/2 mg x naught. So how did I get that? Well, here's the way I got it. First of all, you got to model what the force due to your hand is. Force due to the hand, the magnitude of it is just equal to mg minus kx. This is a constant force mg, which is down this way, and when you're up at this point right here where the spring is completely unstretched, then the force is equal to just mg. In other words, at x equals 0, measuring x this direction, at x equals 0, it's just equal to mg. And when you get down here to the equilibrium point, x naught, then the spring force completely balances mg so that you don't have to put any hand force at all. So when you get to x naught, f of h is equal to 0. So this is the hand force as a function of x. So the amount of work done by the hand force, is just equal to the integral from 0 to x naught of the hand force times dx, but the hand force is opposite the direction of motion, so we'll say minus mg minus kx dx. And when you do this, when you perform this simple integration, you get minus 1/2 mg x naught, where you acknowledge that mg is equal to k x naught. You can work through the simple integral to show that, but that's how that works.